Hello everyone, this is a lecture for Chem 160, and in today's lecture we will be covering kinetic molecular theory, or short for KMT. And you might recall that we want to use KMT in order to understand the phenomenon that we know as pressure. And while we have common experiences with pressure, we need to understand it from a microscopic as well as macroscopic point of view. And let's recall that P for pressure is equal to force over area. Some common units that we may use for pressure include atmospheres, pascals, or PSI. In this particular understanding of pressure, the main thing that we wish to focus on is force. So force is the operative word which we wish to really dive into today. And so we have to ask ourselves, what is force and how do we understand it from a microscopic point of view? Let's recall from Newtonian physics that force is equal to mass times acceleration. And we also want to recall that work is equal to force times the dot product of distance. Let's recall from our physics classes. So let's recall from our physics courses that we have force, which is equal to mass times acceleration. And let's recall that the units then would be equal to kilograms times acceleration, which is meters per second squared, giving us a final value for force of kilograms per meter second squared. And let's also recall that the definition of work is equal to force times some displacement of distance. And again, we know that the units for force are kilograms meters second squared times that displacement in distance, which again is in meters, giving us a final units for work of kilograms meters squared over second squared. So now let's do an experiment where we're taking some gas molecule. In this case, we'll be taking nitrogen, and it's initially at rest with a velocity equal to 0. And we wish to accelerate it and move it to some final velocity. So we're starting off at v equals 0 to some final velocity that we'll call v sub f. And the question will be, what force is exerted to perform work to make a N2 molecule move? And so we need to understand how much energy our N2 molecule will have once we do this work upon it. So now let's look at how our kinetic energy will change once we've done some work on our N2 molecule. And so we'll say delta K is equal to work is equal to our integral of our force as a function of position dx. And so delta K here is our change in kinetic energy. We've got our work right there. And so next what we want to do is be able to make our work on our particle be performed. And how do we do that? One of the first things that we'll be doing is to substitute our force as a function of displacement with our definition for force, which is mass times acceleration dx, and of course we are integrating. We won't be doing any of our integration on the mass itself, so we'll go ahead and we'll pull mass out to the front. And the integration of our acceleration dx. You'll recall that the definition of acceleration is equal to dv over dt, or the change in the velocity over the change in time. So let's go ahead and do that substitution, and we can yield m, our integration of dv over dt times dx. We're going to do some algebraic rearrangement to yield dx over dt dv. So far we've got our change in kinetic energy is equal to the mass integrated from some initial starting velocity to some final velocity. And what we're going to do is we are going to substitute in the definition for velocity, which is dx over dt, times our infinitesimal change in velocity. Once we've made that substitution, you'll notice that we now have m times the integration of v dv. And at this stage, we should be able to integrate from 0 to v final. Once we have done our integration, we'll notice that we should have a mass times a velocity squared over 2, and this is for our final value, minus the mass velocity squared divided by 2 at our initial velocity. And since our initial velocity, was 0, that value then is null, and the overall change in our kinetic energy is now equal to mass times velocity squared divided by 2, or as it's more commonly shown, 1/2 mv squared. Definition for pressure, which is equal to force over area. And since the SI units for force are newtons, and the area we can consider to be meters squared, so we have newtons per meter squared, and so we'll have our definition there for pressure. And that this is also known as a Pascal. So, at this stage, what we really need to be focusing on is the idea of the exertion of this kinetic energy from our gas molecules onto some container. So let's draw this container that contains some atoms which are moving along the path of the container, which we then give it a single axis, which we would call x, and that we have some amount of collisions against that wall. And we're going to make a very odd assumption, and that is going to be that upon the collision we are going to have some initial velocity, Vx, and that after the collision against the wall we will still have the exact same velocity, Vx, of the particle itself, and we know this as a elastic collision, meaning there is no energy transfer between the particle and the container wall. So we need to so with our particle traveling along some space along our box, it impinges upon a wall, and it's going to be traveling some distance L at some velocity which we're currently calling Vx. And so our amount of force of the collisions in time can be described as the force times the change in time, which is equal to the change in momentum, which is equal to 2 times the mass times the velocity. And you might recall that momentum is equal to mass times velocity itself. This factor of 2 that we see in front of mass v sub x is because we will have 2 collisions per each round trip inside of our container. Now let's define a complete trip. So a complete trip inside of our container for our particle should be delta t is equal to 2 times the length of the container divided by our velocity, which makes lots of sense that the faster our particle is going, the shorter amount of time it needs to take to make a round trip itself. And therefore, we've got some average force for our system, which we'll call F bar, is equal to 2 times mvx over 2L Vx. And if we were to algebraically rearrange this, we would find that we have 2 mvx squared over 2L. So we know now that we have this average force, which is equal to 2 times the mass times Vx squared over 2L. But we can also account for the number of atoms inside of our container. And so all we need to do then is to have a multiplicative factor of n, which is equal to the number of molecules in the container. So let's add that factor in, and we would then get n times 2 times the mass times the velocity squared over 2L. You'll notice now that we can cross out our factor of 2 to then yield the number of molecules, the mass times velocity sub x squared over L. And we can now make a new definition for the average velocity, which is currently Vx squared. And we want to make sure that we can account for Vx squared in all directions. And so what we're going to say is that the velocity squared is equal to the velocity in the x direction, plus the velocity in the y direction, plus the velocity squared in the z direction. And then we're going to say that all of them are equal to one another, and we can make a general assumption that now it is equal to 3 times vx squared. We can then simplify that and say that v squared is equal to vx squared. And remember that we just need to divide that by 3. Now upon substituting in for vx squared, we can then yield n times m v squared, which is our average velocity in all directions. There's our factor of 3 times the length of our container. As you can see, the substitution is connected right there, and that we've done the work over here to the right hand side. So we can say right now that we have our pressure is equal to the average force divided by the area by definition, and that we have the number of molecules times the mass times the velocity squared over 3 times L, but now we have to account for the area. And so far we've only been dealing with a one-dimensional box. But now when we account for the overall area, you'll notice that length times area is equal to volume, and gives us a description of a three-dimensional box in which our gas molecules are colliding. So now let's go ahead and substitute in for that definition of volume. Again, we have the number of molecules, mv squared, over 3 times the volume. And you'll notice right now that we have this sneaking suspicion from our mass times velocity squared that we can still bring out kinetic energy and get that factor still in, because basically what we've done is we've just canceled it out. So if we were to pull out kinetic energy here, we will then have 2 times the number of molecules over 3v times 1/2 mv squared. And so ultimately 2n over 3v times our kinetic energy is equal to macroscopic pressure. Why is this result important? This result is inherently important because we are connecting the microscopic kinetic energy with macroscopic pressure. And we can understand this from first principles. And I think that's ultimately important for us to understand that the inherent reason we have pressure is because of the kinetic energy of individual particles colliding on the surface of a container. Okay, so let's write out our recently derived definition for macroscopic pressure is 2n over 3v times 1/2 mv squared for a kinetic molecular gas theory. And so what we're also going to be able to do is define kinetic temperature. We just defined kinetic pressure, but now let's make a connection to temperature itself. And so what we first need to do is define our gas constant, which is actually equal to Avogadro's number times the Boltzmann constant. And so we can substitute this definition into PV equals nRT to get PV equals the number of molecules, and this could be any number. It could be Avogadro's number, but some number less than that as well, Kb times T. And if we were to algebraically rearrange this, we could get PV over n, the number of molecules, kBt. Let's keep that definition in our back pocket because we are going to use it very, very soon. Let's come over here and algebraically rearrange our kinetic pressure equation. And we can also say that P times the volume over N is equal to 2/3 times 1/2 mv squared. We can substitute in our definition for PV over N, which we have over there, and say now that the Boltzmann constant times the temperature is equal to 2/3 times 1/2 mv squared. You'll notice that we can continue to eliminate our factor of 2 to get kBt equals 1/3 times the mass times the velocity squared. It is important, though, for us to re-emphasize kinetic energy constantly throughout this particular lesson as well as others. So let's go ahead, instead of canceling out our factor of 2, keep in our kBt and have our 2/3 times 1/2 mv squared, and we can rewrite that as 2/3 times our kinetic energy. And so again, we can go ahead and solve for the temperature. And how do we do that? Well, we simply just bring over this factor for Kb, do a little bit of algebraic rearrangement to yield the temperature equals 2/3 Kb times the kinetic energy. Alright everyone, so this summarizes the end of our lecture here for kinetic molecular theory. And so we've derived our macroscopic pressure is equal to 2n over 3v times our kinetic energy, which we know as 1/2 mv squared. And then we also have our kinetic temperature, which we now can describe by 2/3 Kb times 1/2 mv squared as well. And so what we can really say here is we can connect both macroscopic temperature and macroscopic pressure with our microscopic understanding of kinetic energy. And of course, kinetic energy is equal to 1/2 mv squared. And so this is going to relate to problems from Tom Brady and our deflate gate problems. And we want to make sure that we stay very cognizant about our units. So in order to do these problems correctly, let's make sure that we use the right units. Mass should be in kilograms. Our volume should be in meters cubed. And we've got N for the number of molecules. Of course, velocity is meters per second. And what's last but not least, pressure should be equal to pascals. Thank you very much for your attention, and please post any questions or comments you have about this lecture. Thank you very much.